Good morning to all. And in today's lecture, in last lecture, we have studied the various topics in robotics, which are introductory. Okay, then basic little bit of history, little bit of how they are classified, and then I have shown you some videos of well-known robots. Okay, the IIT professor. In this lecture, we will look at the main elements of a robot. So, robot is a very sophisticated and expensive equipment even nowadays. Okay, so the components which are required for making a robot, it undergoes some constant improvements and advancements because it is very hard to keep up to the expectations and the demand of the consumer. So initially the motors will have some specifications. Now they are much better. Okay, similarly there were some sensors which you have used earlier. Now they are much better sensors. Okay, within the time span. It is a sort of hard to keep up with all the various mechanical, electronic, and computer or sensing components which go into making up a robot. Okay, the main components are mechanical components, then actuators, transmission devices, sensors, electronics, and computers. Okay, these are some of the key components which go into making a robot. The main mechanical component are links and joints. Links and joints. So link is basically the member which carries a load. Okay, it carries a load which moves, also which positions something or other at the end of the link. So the link should be strong and lightweight. Okay, for example, die cast sections. Again, one sec. Hmm. So as I said, the link should be strong and lightweight. So most of the time they are very lightweight because they are made using die cast sections. Okay, which you have seen yesterday, made up of aluminum quite often. The joints should be friction and backlash free. Okay, it should not have friction and backlash non-linearities. It should be free to extend. Okay, possible, because if you have friction and backlash, the joints will introduce errors which sometimes the controller cannot overcome. Okay, that's the reason why it should not be friction and backlash. The actuators are typically electric, pneumatic, or hydraulic. Okay, and transmission devices are needed to transfer the motion from the actuator to the joint in a proper manner. Okay, so we will look all these components. We will look at the links and joints. We will also look at the actuators. We will look at the transmission devices because these are the main elements of a robot, and then we will also look at the sensors. Okay, the sensors enable a robot. So what is the work of the sensor? It enables the robot to possess touch and feel, also sense motion and forces, and to see and learn. Okay, sensors are required for feedback control. There are sometimes, so these are called as internal sensors also. There are external sensors also, which you can sense touch and force. You can measure the distances, and you can have cameras which can see the environment. Okay, in case of the external sensors, there are also some specialized sensors for welding, painting, assembly, and other industrial applications. So we need to make sure that the weld bed is correct, is of correct height, and we can change some parameters. We can change some of the parameters automatically, or you can see that the welding is happening at the right place. So that is the reason why external sensors are used. So these are very specialized sensors. The computers and software which go into a robot are often more expensive than the hardware. Okay, sometimes. For example, Adobe Photoshop, Adobe Movie Maker, and After Effects, and also AutoCAD. These are very expensive. Even MATLAB. It is sometimes what happens. The device which are we are using for interfacing with the MATLAB is quite cheaper than the version of the MATLAB. This is what the difference between hardware and software. So we have one or more processes to control the motions of the actuators. We sometimes have processors for signals processing and sensing. We also have processors for user interface, data logging, communication, and other activities. So typically in a robot you have a lot of computing power, and there is a lot of software which have been ported on these computers to do a variety of tasks. So we have also offline programming systems with user-friendly graphical user interface. GUI means graphical user interface. For example, your smartphone. So when you click on the menu button, the menu bar opens up. Okay, you can see a lot of applications. When you click on the camera, camera opens up. This is nothing but the user interface. Okay, so it is graphical to train the operator, verify motions, and reduce downtime of a robot. So basically, since the robot is so expensive, we do not want it to be lying idle. Okay, and we do not want the robot such that a robot to be used for training. Okay, now we will continue with the joints. So as I said earlier here, we would like to train the operator in virtual environments such as which is called as offline programming systems. So we have a CAD model of the environment, we have a CAD model of the robot, and we can make this robot move and train the operator in the virtual environment. Now when looking at the joints, as I said, okay, we will look at the joint links, actuators, transmission devices, and sensors in this lecture. So what is a joint? Basically, joint is nothing but an element which connects two or more links. Okay, so you have gone through the definition of joint and link. So basically, what does a joint do? What is the work of this joint? It imposes constraints on the link. Okay, it connects the links. So if you have two rigid bodies in a 3D space, you have six each of them with 6 degrees of freedom. So you have 12 degrees of freedom. If you will now connect these two rigid bodies, okay, using a hinge joint. So hinge joint is nothing but one which allows rotation or relative rotation between the two connected rigid bodies. So in that case, then you have 6 plus 1 degrees of freedom means 7 degrees of freedom. So basically, what has the hinge joint done? Okay, what is the use of that joint in this? It has removed 5 degrees of freedom. So it has imposed 5 constants. Okay, 5 constraints for that links. So hinge joint allows one relative degree of freedom. Okay, so we will look at the these constraints and more detail in this lecture on kinematics of serial robots in the third chapter. Okay, this is the start of the second chapter, and before that, in the second chapter, we will in the third chapter also, or in the second chapter, we will discuss mathematical representation of the links and joints in more detail. So the degree of freedom of a joint in 3D space is 6 minus m. Okay, 6 minus m, where this m is the number of constraints imposed. Okay, so for example, a spherical joint or a ball and socket joint will impose 3 constraints, and the degree of freedom is 6 minus 3 equals to 3, which is very easily known or can be very easily seen. So in a serial robot, as we have seen in the last lecture, this is serial and parallel robot, all the joints are actuated. Okay, and most of the time 1 degree of freedom joints are used. Okay, so in parallel robot or in a hybrid robot, some joints are not actuated and they are called as passive joints, and those passive joints can be multi degree of freedom joints. So for example, in the Stewart platform which I have seen earlier, which so there were spherical joints in that Stewart platform, but they were not actuated. Okay, there was a hook joint, and then that was also not actuated. So only actuated joint was the sliding joint in that case. Now these are some of the typical joints which are used in robotics. First one is screw joint, okay, which is not so common, but sometimes it is used in robotics. Basically, you have one member which is the shaded one, and the another member which is a white portion. Okay, shaded one and white portion. The white portion can rotate and translate about this screw. Okay, so that it so like a normal screw. It is a 1 degree of freedom joint simply because the rotation and the translation are related by the pitch of the screw. You also have rotary joint. Okay, it is 1 degree of freedom joint. Again, we have two members, just like a hinge joint, and second member can rotate with respect to the first member. Okay, so this is theta. Okay, so this is theta is a typical variable which is used to denote a revolute joint. Okay, we also have prismatic joints where one member and slide up. Okay, where you can see here prismatic joint. In this, one member and slide up and slide down with this another member. Okay, and the variable which is used to denote the sliding motion is d. Okay, typically, so we have here a 2 degree of freedom. Okay, so this is a cylinder, and next one is a cylindric joint, which sometimes seen in closed loop mechanism. Okay, where this theta rotation is the rotation, and this sliding d are not related. Okay, there is no pitch, they are independent. As I said, you can also have a spherical joint. It has 3 degrees of freedom. Spherical joint is nothing but a ball and a socket joint. Okay, a ball and socket joint, and this is another theoretical joint which is called as a planar joint. Okay, next one is planar joint. So basically you have two planes, and that is relative 3 degrees of freedom between the two planes. Okay, the second object here can slide in the x and y direction. Okay, the second object here you can see that one, it can slide in the x and y direction, and also it will rotate with respect to the other object. And lastly, we have a hook joint or universal joint where you can have 2 degrees of freedom about the two independent axes. Okay, so there are some of the common, these are some of the common joints which are used in robots and some closed loop mechanism and also parallel manipulators. Okay, now we will go to the links. Okay, introduce in the next videos, upcoming videos, we are going to have a look on the mathematical modeling of the joints and links. Okay, in deep. In this lecture, we are going it with the short introduction. So let us continue. Link is, as I said, nothing but it is a rigid body in 3D space. As far as we are concerned in kinematics, dynamics and control, most of the time in control, it is a rigid body in 3D space. So most robots are rigidly built. We will not look at the deformation and deflection of a link. If you are interested in the space shuttle now, then we need to worry about the deflection. Then the link is no longer rigid. Okay, and we have to introduce this deformation and deflection members of the robot. So a rigid body in 3D space has 6 degrees of freedom. So it can rotate about 3 axes. There are there are three rotation degrees of freedom, and there are three translation degrees of freedom. Okay, so it requires 6 parameters for that. So link of a robot would require 6 parameters in general. However, if the links are connected by rotary and prismatic joint, it is possible to use 4 parameters only to describe the relative motion of one link with respect to the another link, or it will describe one link with respect to the another link. So these are known as Dinavitt-Hartenberg parameters, okay, DS parameters, and they were invented by these two researchers. First one is Dinavitt and then Hartenberg in 1955. So as you can see, this is very useful because almost for the last 65 years they have survived. Okay, if something is not useful, then it would have died a long back time. Okay, and the basic reason why it is useful is I do not want to carry around 6 parameters all the time. If I can get away with 4, it is twice of the third less. Okay, so in a robot you have many rigid bodies. So you can see that if you have 6 rigid bodies connected by the joints, we do not need to worry about the 6 into 6, that is 36 parameters. You can away with 24 parameters. Okay, so these 4 parameters are possible since lines are related to rotary and prismatic joints are used. So we will look at in the kinematics portion in the next chapters. Okay, so what are the DH parameters and how to find the DH parameters? Okay, so what are the exact definition of each of these DH parameters? 4 DH parameters. So for multi-degree of freedom joints, if you have a multi-degree of freedom joints and you want to use these DS parameters, then you have to replace this multi-degree of freedom joints with 3 or more multi, okay, 3 or more than 1 degree of freedom joints. Okay, so for example, if you have a spherical joint with 3 degrees of freedom, you can use 3 equivalent rotary joints. Okay, and so this is a good thing to do. So this is a very nice approach. It has a lot of advantages. We can get roll of we can get roll which 4 parameters. Okay, with 4 parameters. Unfortunately, there are several DH convention possibles. Okay, and many textbooks will have one way to describe the DH parameters, and some other textbooks will have another way to describe these parameters. So it turns out is that what happens when you go from 6 to 4, you have several possibilities. Okay, now we will be using this DH convention. Okay, in the next upcoming chapters. Okay, deep conceptual study regarding this. Now you can see here. So let us look at this robot. Okay, you can see that this is a Puma 560 manipulator. So what do we really mean by this? Okay, how do we really describe this? This is a very brief introduction. We will look at all these things in much more detail again in the third chapter. Okay, in kinematics of serial and parallel robots. So in this Puma robot, we have 6 joints. Okay, so one rotary joint is here. Okay, one rotary joint is perpendicular to the vertical joint. There is a third rotary joint here. Most of the time we will see Z1. We can see if I will zoom it out. Hmm. So most of the time we will see this Z1, then again Z2 and Z3, denoting the joint axis. Okay, and then there are these rotary joints which are intersecting at this point. This is also sometimes called as the wrist point. Okay, So we have Z4, Z pi over here. I can barely see it. Z4, Z pi and Z6. Okay. Hmm. Which is which are intersecting at the same place. And as you will see in more detail later in the DH parameters. Okay. So there are distances also like A1, A2, and A2, D3, A3, D4, and so on. Okay. These are link length, okay, offsets. And you will also have some twist angles. So the angle between joint 1 and joint 2 is one such parameter. Okay. In this case, it has been built with 90 degrees. Okay. Built so that they are 90 degrees to each other. So we will have all the four parameters which we will describe in more detail, okay, in kinematics. Interesting thing is this is that design is that it has the last three joint axes intersect at one point, and this gives a lot of advantages in the modeling and also analysis of the robot, especially in kinematics analysis. So here, as I said, there are these four DH parameters. Okay, most of the time these four DH parameters are given in the form of a table. Okay, so these are the four DH parameters. So in this table, what you have is I. It is the link number. So these are 1, 2, 3, 4, 5, and 6. Okay, the Puma has 6 links. Okay, this is for the Puma 560. And along the row, you have this AI minus 1. Okay, again this AI minus 1, then DI and theta I. So these are the four DH parameters for each link. So for example, of the third link of this one is 0. Means for the third link, this parameter is 0. Okay, it is some quantity A2 in this for this parameter. It is a number to the distance D. Okay, in DI it is a distance. In case of DI for 3 it is 0. For third link it is 0. Okay, for third link this is 0, this is A2, and this is A3. Another distance, for another distance it is theta 3. Okay, which is the rotation of the third link. So it is a joint variable. So in this Puma, all the joint variables are rotary. Joint variables which are represented by theta. So I discussed, okay, this I also told you earlier. We have theta 1 to theta 6 as 6 joint variables. As you can see in this DH table, many of these alphas are very simple. It is either 0 or plus pi by 2 or minus pi by 2. Okay, and this is how most robots are designed and built. It could have been 30 degrees, 22 and a half degrees, but normally as a designer we pick these nice simple parameters. Okay, so when you buy a robot you will get a table like this. So for any robot basically they will give you the DH table for that robot. So if you have 6 degrees of freedom robot, you will get a table with 6 rows. If you have 4 degrees of freedom robot, then you will get a DH table with 4 rows. Okay, this is supplied by the manufacturer, who in turn has the obtained it from the design of that robot. So let us continue with the actuator or the main elements of the robot. Okay, first one is the actuator. The actuator are required in a robot to move the joints, also to provide the power and to do the work. So in serial robot, actuators must be of low weight. Okay, why? The reason, because the actuators of the far away links are distal links. Okay, and these are needed to be moved by the actuators near to the base. Okay, so that is in the case of the Puma robot. The actuator which is designed with this fourth joint must be moved by the first joint. So if you have a very heavy actuator sitting on this fourth joint, the first joint will have to do a lot of work, as we know. Okay, it has to put a lot of effort. It needs to be very powerful. So we need actuators which are lightweight and high power in case of series. Okay, the actuators are distal. The actuators are the distal links need to be removed by the actuators. Okay, near to the base. In case of parallel robot, actuators are at the base, so we do not really have to worry too much about moving the actuator. Okay, moving the another actuator. So the actuator drive a joint through a transmission device, which and we will come to that. Okay, so motor most often is not directly connected to the rotary joint. There will be some in between device which is called as a transmission. Okay, and there are three main types of actuators. Okay, first one is the hydraulic, pneumatic, and electric motors. So there are these are the some pictures of typical actuators. Okay, on the top left here, this is a pneumatic actuator. Okay, so basically in a pneumatic actuator we have some reservoir where compressed air is kept, and you can see here it is a reservoir as a tank where compressed air can be kept, and then you have some kind of valve, then you have some kind of regulator and a solenoid, and then this let us in the air into this actuator. So when the air is let in this end, okay, the air is let in this end, the end will go in and out. Okay, sometimes you have inlet at two places, one to send it and in one direction, and one to send in the another direction. So the hydraulic actuator is something very similar, except instead of air you can have compressed oil. Okay, so hydraulic actuators can transmit much more force. It has much more power because air is lightweight and it is compressible, whereas oil is incompressible. We can also have a DC motor. Okay, so in this, okay, you can see here this is a nice picture of DC motor showing all the parts. So basically we do have a rotor which is not really seen here, which is most of the time a permanent magnet, and then on top of that we have a stator which is coils. Okay, so we send current to these coils due to the Faraday's law of electromagnetic induction. The rotor, which is permanent magnet, will start rotating if the direction of the currents are changed. Okay, we also have a device called as an encoder. Okay, so encoder will measure the rotation of this rotor shaft, because in control we need to know how much the motor is rotating. Finally, we also need reduce somehow to reduce the speed of this shaft. Okay, so in typically a motor will rotate very fast. It may rotate up to 2000 rpm. Okay, even above that. You cannot connect the shaft of the motor directly to the joint. So for that encoder is used. There is most of the times there is some kind of transmission devices. So in this case, what is shown is gearbox, which will reduce the speed of the output shaft. Okay, you can see here the gears, internal gearbox. Okay, so the electric motors or electromagnetic actuators are widely used in robots. Okay, even from the earlier stage, they are readily available in various variety of shapes, size, and power and torque ranges. Okay, they can be very easily mounted or connected to the transmission elements such as gears, belts, and timing chains. Okay, they are also amenable to modern day digital control. Okay, it is compatible, so they are They have an encoder which measures the rotation, because as I said earlier, the shaft cannot be connected to the joint. Okay, and we will see that later in this measured that that this measured rotation of the shaft can be used to control the rotation of the motor by the encoder. Okay, or the speed of the motor shaft. So there are three main types of electric actuators which have been used. One is called as stepper motor. Second one is permanent magnet DC servo motor, and there is something called as brushless DC motors. Okay, in a brushless DC motor, the currents are not switched in the direction you want. Okay, by means of brushes, which is done electronically. So the stepper motor is normally used in small robots. It's small payload and low speeds. Okay, because of stepper motors cannot provide too much torque. Okay, or cannot operate at very high speeds. Stepper motors are typically permanent magnet. Okay, also hybrid or variable reluctance type. Okay, so these are some terms which are in common in the stepper motor literature. A stepper motor, as you can have a look, is typically actuated by a sequence of pulses. Okay, so for a single pulse, if I give a single square wave, if I give a single square wave, a single pulse, then the rotor will rotate by one step. Okay, either square wave or a single pulse. And how does it rotate? How much does it rotate? Okay, so the steps are such that the rotor and the stator will become aligned at the end of the step. So the typical step sizes in a stepper motor at 1.8 degrees, okay, or 0.9 degrees. Okay, these are the steps. So every time you give a step, it rotates by 1.8 degree or zero point 0.9 degrees. Okay, and the speed and direction of this stepper motor output shaft can be controlled by the frequency of the pulses that we have given. Okay, either square or single pulse. So if you want to rotate very fast, you get these pulses at a higher frequency. One of the advantage of a stepper motor is that it can be used in open loop. Okay, so what is the reason why it can be used in the open loop? Because there is no cumulative error. Okay, there is no cumulative error. The maximum error in a stepper motor is typically one step. So it will be maximum 1.8 degrees or zero point 0.9 degrees depending upon the step size in a stepper motor. So a stepper motor can also be used in micro stepping mode. Okay, so basically what is micro stepping now? So we do not want 1.8 degrees, but let us say we want the 1/10 of this 1.8 degree, that is 0.18 degree. So this can be achieved. For that we need to closed loop feedback control. Okay, and when you do micro stepping, there is a loss of torque in the stepper motor. So most of the time, so this is a typical picture of stepper motor. I'll zoom it for you. Okay, you can see. So there is a rotor which contains all these teeth. Okay, then there is a casing, motor casing, and there are the stators with coils. Okay, so schematically, what is shown here is the rotor with number of teeth. Okay, which are the magnets, and the stator with the coils. These are the parts of a stepper motor. So basically, what happens is here electromagnet electromagnet is activated. The rotor rotates such that the nearest teeth, okay, the nearest teeth will be line up. So here you can see. So electromagnet 1 is activated. Then the rotor rotates up such that the nearest teeth line up. Okay, if electromagnet 1 is activated or deactivated and 2 is activated, okay, then the rotor rotates such that again the nearest teeth line up. Okay, and this rotation is a by a step which is typically 1.8 or 0.9 degrees. If electromagnet 2 is deactivated and 3 is turned on, again it will rotate by one step again. Okay, till it teeth line up. Okay, another teeth line up, and so on. So it keeps on activating and deactivating at each time there is a step which is done. Okay, so permanent magnet stepper motor is similar to variable reluctance stepper motor. This is the variable reluctance stepper motor which is shown here. Okay, except the rotor is radially magnetized. So instead of these teeth or magnetized teeth, we have these radical, or we have this radial magnetization, and we can also have hybrid stepper motors. Okay, which basically combines the best features of this variable reluctance stepper motor and permanent magnet stepper motor. Okay, so we can also have a DC or AC servo motors. So a rotor here is a permanent magnet again, and the stator is a coil. The permanent magnets are here typically made with rare materials, okay, different materials like samarium, cobalt, neodymium, okay, which can provide large magnetic fields, also with high torques, okay. So and various other also rare earth materials which can be used to make very strong magnets, okay, which can get very powerful magnetic fields, okay. So commutation here is done using brushes, or in case of brushless motors using Hall effect sensor and electronic devices. Okay. So as I said, if you have brushes, then the brushes is saturated. It is a standard DC motor. Okay. Okay. This is a standard DC motor. You can change the direction of the current because the brushes work in a way that you can also do this commutation using Hall effect and electronic devices. These are called as brushless motor. So in a DC actuator, okay, in a DC actuator, a DC servo motor actuators are widely available in large shape, okay, large size and power. Also torque range are very high, and these are very reasonable nowadays. So it is easy to control because most of them come with the optical encoder, or we can fix an optical encoder at one end. We can also attach tacho generator which mounted in line with the motor shaft, and then we can measure both the rotation as well as the velocity, okay, and the speed of the motor. So the brushless AC and DC servo motors have very low friction because there is almost nothing in contact. They also have very low maintenance, okay, low cost, and they are robust. So most of the time nowadays the trend is to use the brushless DC motors, okay, also sometimes called as BLDC motors. So again, in case of, you can see the DC servo motors, okay, different types of DC servo motors. So these are the well-known features of DC motors, out of which this is an interesting motor. Okay, these are called as small RC servo motors. This is very interesting. These are toy motors. Okay, these are very originally made for remote control toys. Okay, you can also have seen in your toys if you have played or you have opened your toys. Okay, that is why the word RC comes from. Okay, so RC servo motors, and they are very easily available in the internet. Also, these are some well-known companies like Pitman, and there is also some other companies which makes this DC servo motors. Okay, DC brushless motors. This is another interesting DC motor. Okay, that is what is used in electric bikes and cars. So most of the time, okay, that this is one brushless hub DC motor. Okay, it can be used in electric bikes and cars. So most of the time we have seen, so most of the time sorry for the delay. So most of the time we have seen that the rotor is inside the stator, Okay, the rotor is inside and the stator is outside in this case. So we provide current to the stator, and in that inside the rotor it will rotate. So in a bike, electric bike, we can invert it. So the stator is inside and the rotor is outside. Okay, so we provide current to the stator, and the rotor is basically on a wheel is mounted, it will rotate. This is the basic mechanism of a hub motor. So as you can see this, it looks like a hub, and we can mount the wheel on the top of this, and when you provide current to the stator, now the rotor which is outside it will rotate, and they come with a variety of ranges which you can get. For example, some 24 volts, 48 volts, 60 volts, various kinds of DC voltage which needs to be applied, and then the wheel will rotate, and they can be directly used in electric bike also, nowadays in electric cars. This is also sometimes called as the hub motor. So why it is called as hub motor? It indirectly fit into the hub of your bike. So now, as you have seen the difference, DC motors, okay, brushless DC motors, servo motors. So now, how is the DC motor normally driven? Okay, I will zoom it. So how it will work? Okay, normally. So basically, what we have is we have what is called as a PWM circuit. Okay, here one. So what is PWM circuit? Okay, we provide a pulse of 0 to between 0 and 12 volts. Okay, and we modified the width of this pulse. Okay, so for example, if it is on for T1, okay, for T1 period it is on, and it is off for T2, then we will get some average voltage. Okay, if it is on for full length of time T, then you will get 12 volts which you are applying to the terminals of the motor. So this quantity T1 divided by T1 plus T2, here you can see, is called the duty ratio, and by changing this duty ratio we can give different average voltage to the motor. Okay, and this step is done at very high frequency. So the advantage of this is that we are only not changing the actual voltage, we are applying, okay, but we are changing the duty cycle electronically. So that is why this is called as the pulse width modulation. Okay, you are also learned this in the modern power electronics. Okay, and most of the people, I think, they are working on this in their dissertation. The way to drive this DC motor is basically using something called as a H bridge. Okay, now you can see here H bridge. So we have transistors and we have an input which is forward and reverse. Okay, two inputs, and then we have this arrangement which looks like a H bridge. Okay, so if the input is 0 and this also 0, the motor will be off. Okay, input A and B is 0, motor will be off. If the input A is 1 and input B is 0, the motor will rotate in forward direction. So then the current will go such that the motor will rotate in only one direction. If you switch the order of the input, and you can make input A 0 and input B 1, then you will go in reverse direction. Okay, and you cannot have both inputs. So basically what you are doing is by switching input A and B from 0 to 1 and 1 to 0 again and again using digital control. The whole idea is we want to do everything digitally. Okay, then we can make the motor go forward and backward or to be off. Okay, so these two things enable a DC motor to be controlled electronically. You can control the speed of this motor by modulating the width of the pulse in PWM, and we can change the direction by switching the two inputs in the H bridge. Okay, so these are the two methodologies. Okay, for the DC motor drive for DC motor. So next one is transmission used in robots. So let us continue here. Let us look at the transmissions which are used in robots. So the purpose of a transmission is to transfer power from the source to load. Okay, it is also to transfer the power at an appropriate speed. That is very important. Let us take an example. So typical rated speed of a DC motor is between 1800 to 3600 rpm. Okay, so for the sake of an argument, let us do our quick calculation. Let us assume that the rated speed of DC motor is 3600 rpm. Okay, which is nothing but 60 rotations per second, which is roughly equal to 360 radians per second. Okay, so I'm assuming pi in this case as 3. Okay, for a typical 1 meter link, if you connect this motor to a 1 meter long link, okay, the tip speed will be omega into r. Okay, that is the 360-degree radian. So you will get 360 meters per second. This is really high. Okay, so it is in fact greater speed than the speed of sound. Okay, so hence we require a very large speed reduction. Okay, and that is the reason one of the purpose of the transmission is to transfer power at the appropriate speed. Okay, so what is the typical appropriate speed? Then question arises. So speed. Okay, so instead of 60 rps, we probably need to know 60 rpm. Okay, or 1 divided by 60th of this. Even then it is like 6 millisecond meter per second, which is not a good idea. Okay, so we need even smaller, more speed reductions. Transmissions can, if needed, also convert rotary to linear motion. Okay, so sometimes you have a motor, but I want to implement a prismatic joint, sliding joint, that can be done by using what you call it as a ball screws. Okay, where the nut of the screw moves up and down. Okay, when you rotate the inside. Okay, so transmission also transfers motion to different joints and to different directions. Okay, so I can have one motor in one place, and I can use belts and chains and some other kind of transmissions. So the transfer so to transfer the motion to some other joint at some far away place, not a very far away, at a distinct place. Okay, so transmissions used in robots. So transmission are these transmissions are decided based on the motion, load and power requirements, and by the placement of the actuators which are relative to the joint. What are some of the desired types? Okay, so it should be stiff. First of all, it should be of low weight, it should be backlash free, and it should be more efficient. So direct drive motors directly connected to the joint are sometimes used in this case. It has advantages of low friction and also low backlash. Most of the time, whenever you have a transmission, okay, you are introducing friction and backlash, but these are very expensive. Okay, so typical transmissions are gearboxes, okay, of various kinds like spur, worm gears, worm wheel, country gears, etc. We can also have belts and chain drives. We can have harmonic drives for large speed reductions. We can have ball screws and a rack pinion, okay, drives to transform rotary to linear motion. And sometimes we also have kinematic linkages. So we can have a 4-bar linkage to transmit the motion from a motor to some jaw for a gripper. Okay, so now transmission used in robots here. So this is an example of a harmonic drive. Okay, basically in harmonic drive we have two flexible members which are called splines. Okay, circular splines. Okay, and because of this flexibility, you can get very large speed reductions. We can have very sophisticated gear reduction mechanisms here. So this looks like a cutout view of gear reduction mechanism with lots of ball bearings and some gears and various other things. Okay, this is a picture of ball screw here. So basically you have this screw and this is a nut. Okay, and this is nut, but in between the nut and the screw there are these balls. Okay, you can see here, and the advantage of these balls is that it reduces the friction dramatically and drastically. As I said a few minutes back, that you can have a 4 bar mechanism, okay, to move the jaws of a gripper. So when I rotate this motor, and if you have this 4 bar mechanism, one link, two link, and so on, and if you move these jaws, you can move parallel to each other, which is of advantage. Okay, so we want to grip an object. If we want to grip an object, we want the jaws to move parallel to each other. Okay, here you can see that. So if you want to grip an object, we want to jaws, we want these jaws different to move parallel to each other. Next, we come to elements of a robot, which are sensors. Okay, so a robot without sensor is like a human being without eyes, ears, and sense of touch. Okay, so a sensorless robot requires costly, time-consuming programming. Okay, because it is not consisting of sensors. It can perform in a playback mode. Okay, repetitive mode. If you do not have sensors, it cannot adjust the change in environment, tooling, okay, and workpiece. Okay, if the tooling and the workpiece has changed, we cannot account for it in the robot. Sensor will constitute the perceptual system of a robot. Okay, they are designed to make inference about the physical environment. They are designed to navigate and also localize the robot by itself, and they respond more flexibility, okay, to events occurring in the environment. Okay, so if somebody comes in front of this mobile robot, okay, it will stop. When the person has moved away, it can resume its path. Okay, so sensors are designed to enable learning, thereby endowing robots with intelligence. Okay, also sensors will allow less accurate modeling and control. Okay, so time consuming and iterative time will reduce, programming time also reduces. We will see later it on. Okay, and some sensors are enable robots to perform complex and increased variety of tasks reliably, thereby introducing the reduced cost. Okay, so now let us continue from here. There are two main categories of sensors in robots. These are called as internal and external sensors, as I told you in the start of the lecture. Okay, so the internal sensors are measured variables for control. Okay, measuring variables. So internal sensors will measure variables. Okay, for control. So we need to measure the joints position. We can use what are called as incremental and absolute encoders for that measurement. We need to measure the joint velocity. This is measured using something called as tachometer. Okay, we often need to measure the joint torques, also the force with the robot that is applying to the environment. Okay, there is something called as the force torque sensor. Okay, force torque sensor in the market, which we can mount at the wrist of the end effector. Okay, so position, velocity, and force are often used to control the robot to achieve the desired task or to apply the desired force. We also have sensors which are called as external sensors. Okay, these are basically proximity. Okay, we want to detect something very close to the robot. If you want to detect something very close to the robot, we will also want to detect slip. So if the robot is gripping something object, how do we know that it is gripping properly and that is not slipping. Okay, for that purpose external sensors are required. We also need to measure distance from of the robot from an obstacle or from some other robot which we want to go towards or we want to avoid. Okay, and there is this thing called cameras and vision sensors, okay, which are very powerful external sensors. A camera can be used for the wide variety of tasks. Let us look at the optical encoder. Okay, now this is the basic schematic principle of optical encoder. So now optical encoder consists of the following items. So basically there is an LED, okay, one or more LED will be there, and then there is a photodiodes here. Okay, there is a transparent disc. Okay, and on it we deposit by etching or photo depositing patterns. Okay, so most of the time these patterns will be stripes or dark stripes. I can You can see here, or depositing patterns. Okay, so you can have some other patterns also, especially in absolute encoders. So now let us connect this disk to the motor shaft. Okay, so when we connect this disk to the motor shaft, so when the motor shaft is rotating, the light from the LED will be alternatively obstruct by these dark stripes. Okay, and the photodiode we get will get a signal here when it is obstructed, so that this is the signal that we measure. Okay, this is the signal that we measure. So we count the number of pulses at the photodiode, and as you will see little later from that, we can find the number of rotations, also the amount of rotation and even the direction. Okay, so this is one of the most important and widely used internal sensor. It can measure the rotation of the motor shaft. As I said earlier, it consists of an edge encoding disk, okay, with photodiodes and LEDs. This disk can be made of glass, plastic, or even metal. Okay, as the disk rotates, light is alternatively allowed to reach the photodiode, okay, resulting in a digital output similar to the square wave. This is how the optical encoder works. So this is what it looks like. Okay, this is what the output looks like. We will see it in a clean manner. So there are typically it has encoded three outputs. Okay, one is called as A, B, and I. Okay, one three outputs. One is called A. So you can see one square wave. Another is called B, which is lightly shifted. Okay, forward. A and B are more or less similar, but just shifted for by some distance in time. And then there is something called I. Okay, this is also called as the index pulse. Okay, so channel A, B are typically available. A and B are phase shifted by 90 degrees, and I is called as the index pulse. And this is obtained when the disk completes one full rotation. Okay, so every time you get an index pulse, you know that the disk has completed by 360 degrees. Okay, or rotated fully by 360 degrees. So as you can see from this A and these signals A and B, the pulses are counted in A microprocessor. Okay, so depending upon A and B, the number of pulses tells you how much it has rotated and which one is leading. If A is leading, okay, then B is rotating in the one direction, and if B is leading, then A is rotating in the opposite direction. So this is an encoder which is sometimes called as incremental encoder. We can also have encoders which measures the absolute rotation. Okay, we can also use these signals to estimate the velocity. But why? Because if I say that I'm getting 20 pulses in, so let's say some time. So what is the estimated speed? It is 20 into something which gives you the amount of rotation of divided by theta t. Okay, so that will give you the velocity. So it is very often used to estimate velocity also. Next one is, now we will have a look on force torque sensors. Okay, so this sensor is used to measure the forces and moments which are acting at the end effector. Okay, or at some other points like the wrist. So we can either measure these forces and torques at the joint and the wrist. So the force torque joint sensor, you can estimate the torque by strain gauge and joint itself. Okay, so there is a motor, there is a joint, maybe there is a transmission in between the transmission in between the motor and the joint, and I can set up something with a strain gauge which will tell you how much is the torque which is the motor is supplying by measuring some output from the strain gauge. The force torque wrist sensor is more interesting. Okay, it is mounted between the end arm and the end effector. Okay, mounted between the end arm and the end effector, and it can measure all six components of force, okay, and torque using strain gauges. It is extensively used in force control. I would like to control the forces which the end effector is applying to the environment. Okay, and in any control, if you have to measure and use a feedback, this force torque sensor is used to measure the force, and then this feedback control is used to make such sure that the desired force or torque is applied. Okay, so the performance specification to ensure that the wrist motion is generated by the force torque sensor do not affect the position accuracy of the manipulator. This is very important. Okay, so if you are going to mount a force torque sensor at the wrist, it should not affecting the kinematics. Okay, it should not say because of the force torque sensor some error in tracking is introduced. Most of the time such a force torque sensor which I will showing you is the next made from single metal block to avoid hysteresis. Okay, now here you can see. So how does it looks like? Okay, so the force torque wrist sensor consists of a block like, okay, this is this white here is connected, okay, to the end effector, and the outside here is connected to the body of the robot or to the other part of the robot. So basically, if you let us say you are taking some tool here, let us say a wrench or a screwdriver which is connected to this white portion, and some force and moment which are applied to this wrench. Because of these members in which we mount some strain gauges, these columns or these beams will deflect. Okay, because the force of which is applied at this white region. Okay, and by measuring the strains we can find what is the force and the torque which is, okay, which this end effector is applying to the rest of the body. So now here you can see the z the z axis. Okay, z axis as there are shown this way. So I can apply a z force. I can also apply a mz moment here. Likewise I can have a fy. Here you can see f suffix y force and my force and mx moment. Okay, here, and fx force. Okay, we have 8 strain gauges. So we have w phi, okay, which is on this face, w6 which is on this face. Okay, w5, w6, w4 and w3, w4 and w3 at this face, where W2 is at this phase, W1 is at this phase, W7 is at this phase, okay, and W8 at this phase, okay, and so on. So if this bending is about the, if there is a torque bending which is about this axis, there is a force acting here and a force acting here. So the strain gauges W4 and W8 will see large outputs because there is no bending on the other phase. Likewise, if the Fz is being applied, then you can see that the second strain gauge and the fourth strain gauge is the one. Okay, the eighth strain gauge which is one and the sixth strain gauge which is one. They will see the Fz force. Okay, and likewise for fx, fy, mx, my, and so on, I can find a relationship between the six components of force and moment. Okay, so that are fx, fy, fz, mx, my, and mz, which is the variable f, and the strain gauge readings which is there are eight of them. Okay, which are w1 to w8. Okay, and find a relationship between the strain gauges values and the external force. Okay, so let us just check once. Suppose I am applying Fs here. I am applying Fx, which is in this direction. Okay, so which strain gauge will see the maximum output? It will bend in this direction, right? It will bend like this. Okay, so this W3 and W7, okay, W3 and W7, okay, will see maximum output. The others will see very small output, basically due to coupling. So you will have a non-zero elements, that is R13 and non-zero element R17. Okay, likewise all others. So again, suppose let us see what happens when you have my. Okay, this my. My is a moment about y-axis. So if you have moment about this y-axis, you can see that W2 and W6, W2 and W6 outputs will be large. Okay, so we can fill up this matrix with some variables. Okay, and then these quantities can be obtained using calibration. So you apply at a known force fx and see what are the values. Okay, and so on. So once you have calibrated, then this R matrix is known. Okay, and then if you measure some strain gauge readings, you can multiply the strain gauge readings with that R matrix and obtain the fx, fy, fz, mx, my, mz. Okay, transpose. So if so, this is the basic idea of a force torque wrist sensor. Okay, by measuring these strain gauge readings, you can find the external force that the robot is applying. So now we will move towards the next one. I think there is no need of this FEA analysis. Okay, Steward platform, it is based in the ISC. So and this is quite complex. So we'll skip this part. Okay, on this slide. So let us continue here. Let us look at the sensors in robots which are external. Okay, so we have seen internal till now. We will see external from this. So what is the purpose of external sensors? Okay, to detect the environmental variables for robot guidance, object identification, and material handling. Okay, so if I want to see that whether the correct object is there, and they and I can command the robot, okay, to go and pick it up. If the correct object is not there, I cannot identify the object maybe, I do not want the robot to go to that place. So there are two main types of contacting and non-contacting sensor. Okay, the contacting sensors basically respond to physical contact. So they are touch sensors, basically some kind of switches and photodiode. Okay, and also LED combinations, which can also measure slip and also measure touch. Okay, basically we have resistive and or capacitive arrays, and you can feel the environment. Okay, we can feel whether it is rounded or some other shape. Non-contacting sensor. Okay, it detects variation in optical, acoustic, and electromagnetic radiations or change in position, also orientation. Okay, so we can have proximity in this case. There are various kind of proximity which are inductive, capacitive, optical, ultrasonic, etc. You have range sensors which can be capacitive and magnetic. Okay, it can be a camera. You can also use sonar. Okay, sonar for the ocean purpose. Okay, which ships are using. You can use a laser range finder. You can also use some thing called as structured light. So I will show you few of them. You can also have color sensors to detect the color of the object. So we are not going to discuss this in detail. Okay, and then we can measure speed and motion of the object in the environment. Okay, so there is something called as Doppler radar. Then we can have a camera. We can also have accelerometer. Okay, then we can have gyroscope. Accelerometer and gyroscope can be used to measure the speed and the angular velocity, or linear accelerometer and the angular accelerometer of the object. Okay, this accelerometer and gyroscope is pre-installed in our Android smartphones. Okay, featured phone, if you can see while playing the games. Okay, we can also do identification of the object, that we can again use a camera for that. There is something called RFID. Okay, so we can have tags on the objects. We can read the tags using the radio frequency ID and figure out whether it is the correct object or not. We can have laser ranging and we can have ultrasound. Finally, we will have localization. Okay, I want to know where my robot is in the workspace or in the environment. So you can either use compass for that. We can use odometer. Okay, it is a if it is a mobile robot, you can count the rotation of the wheel and figure out how far do your robot have been traveled. You can have GPS for that, and you can also use camera. So as you can see, camera is very useful. It can be used in many such applications. So now we will quickly go through some of these common sensors. Okay, so if you want a touch sensor, so basically what do we have? We have a micro switch and a LED photodiode. Okay, so in this section, so these sensors allows you to touch, feel, see and locate the object. Okay, so if there is an object in this finger mechanism, and if it touches, you will get a signal from these micro switches. You can also see that this light beam will be blocked, and you know that whether the object is inside the fingers or not. Okay, there is a simple LED photodiode pair here that is used to detect the presence, okay, absence of the object to be grasped or to be caught. So I would like to know whether the object is there before I would command the robot for that to grip or grasp. So when do you stop? So when the micro switch detects it has touched, okay, then it will stop. You can also have external sensors which are also measures slip. Okay, you can see here. So basically it is again like a gripper, but inside the gripper that, okay, that are like an object here. Yeah, there is a dimple ball. Okay, so the actual object is here, and in this dimple ball it is connected to a disc which can rotate. Okay, so when the ball rotates, the disc below here can touch some contact points here. So if the object is slipping in this direction, okay, then the contacts will be here. And if the slipping in some other directions, you have some other contact. So a slip sensor is basically used to detect if the grasp object is slipping or not. It is a free moving dimpled ball. It deflects a thin rod on the axis of conducting disc. Okay. Eventually spaced electrical contacts placed under the disc. This is the schematic. Okay. It is much more compact. If the object slip past the ball, the moving rod and the disc, electric signals from the contact to detect the slip are obtained. Okay. And the direction of slip is determined from the sequence of the contacts here. Again, tactile. Okay. So you can also have what are called as tactile arrays. Okay. So it is a skin like membranes to feel the shape of the grasp objects. I think you have seen this in case of the robots for surgeries and holding the objects. You can also use to measure force torque required to grasp this object. And basically, as I will show in the next slide, there is a change in resistance or capacitance when you apply pressure on this object. Okay. And that change in resistance or capacitance is used to feel that shape of the object. Okay. Now externals again here, tactile sensor. Okay. So typically a tactile sensor consists of a thin rubber skin, okay, which is on the upside. There is a set of electrodes which we call as X electrode, okay, X and Y electrodes, and another set of electrodes which are perpendicular to this called as the Y electrodes. Okay. So we send current through one set of the electrodes and we can measure in the other set. Okay. So basically what happens is that the magnitude of the current is proportional to the change in the resistance due to the deformation of this piece of this conducting material. So if there is an object which is sitting here and you are gripping it, okay, it's some, okay, you are gripping it, some points between the X and Y electrode will be shorter than the other points. Okay. So the resistance between say this point and this point is different than the resistance between the point and the some other point below, and that is seen by the change in the current when you can see this Y electrodes. Okay, the current is going through the X electrode and you can scan the Y electrode. So in some places the current will be smaller, so it is also, you can sense the change in capacitances. So if this material changes capacitance when you compress it, okay, we can also use that. So these are sometimes called as artificial skins. Okay, these are a lot of, there are a lot of attempts for artificial skins using our other physics. So we can have a filled, okay, fluid filled membrane, and when you press the fluid, it will change the shape of the membrane. It will change, and from that you can find out the shape of the object. We can also have what are the called as Hall effect sensors, and we can have an array of these Hall effect sensors, which also tells you how, where there is contact or where there is a pressure. We can also have MEMS sensors. Basically, there is a silicon pieces which are micro machined and doped with strain gauge flexure. Okay, it is basically, so it is like basically not such strain gauges which, and when you see and when you use this sensor, it can tell you where the strains are difficult and the strains are different. Okay, wherever there is pressing or wherever there is deformation, and whether there is a deformation, you have several such points, you can get an idea of that shape of the object. So these tactile sensors allow you to touch, feel and sense the shape of the object that you have grasped. Next one is proximity. We can also have external sensors which can detect the proximity. Okay, so it detects basically the presence of the object or an object near to the robot which is of large, which is not for large distances. Okay, so it works for very short ranges between say 15 to 20 millimeters. For example, in your mobile phone at the speaker, okay, at the call speaker, there is a proximity sensor, okay, light transmitting and receiving register. So whenever you take your mobile or smartphone to the near to the ear, it will turn off the screen. Okay, it will sleep the screen. That is called as the proximity sensor. Okay, it is used in order to avoid the manipulations and disturbance to the calls. Okay, because that the pressing of the buttons like hold and cancel due to the cheeks and skin can be neglected. Okay, it is frequently used in stationary and mobile robots to avoid obstacles and for safety during the operation. These are four main kinds of proximity sensors. Okay, you can have inductive, capacitive, ultrasonic, and optical. Okay, so in case of inductive proximity sensor, basically consists of a coil and a magnet. So if you bring these objects closer to a steel or an iron or a ferromagnetic object, the field line will change and you can sense the change of the field lines in this coil. So for example, it could be like this coil seeing, okay, you can see here, it could be like this, the coil is seeing nothing when you are bringing something. Okay, you can see some intersection of the coil with the field lines. Okay, here, so the change in the flux introduces a current pulse with amplitude and a shape proportional to the rate of change in the flux. Okay, so we can get an output which looks like this. Okay, when you bring this magnetic inductive sensor closer to a ferromagnetic object, so if you bring this slowly, the voltage will be lower. Okay, then if you bring it at high speed, the voltage, okay, so typical response is that it works only if very close by. Okay, so if you have some plot, if you go far away from the object, okay, the output is very low, like here. So this is very useful where access is a challenger. Okay, next one is capacitive proximity sensor. Okay, so you can have capacitive proximity sensors also. Basically it consists of a reference electrode, okay, and an active electrode. In between we have air, and then we have sealed, and then we have some circuits inside. So basically if you bring this electrode which for which there is a voltage which is applied, okay, and you bring it near to an object, that equivalent capacitance between these electrodes and the outside will change. Okay, so the change in capacitance can be sensed with the distance. So if it is like far away from 15 to 20 millimeters away, then the change in capacitance will be very small. But if you bring these active electrodes very close to an object, then the capacitance will be much more larger. Okay, it is very similar to this magnetic inductive idea. Okay, except it is used for electrostatics. It can sense metallic as well as non-metallic objects. Okay, as I said earlier, there is a reference electrode with some voltage. Okay, there is an active electrode, there is an electrostatic, so some capacitance is there already. So when you bring it closer to an object, the capacitance changes and you will get a different voltage. You can see the voltage change in capacitance. Okay, so as I said, the object's entry in the electromagnetic static field of electrode changes capacitance. Okay, so oscillations will start once the capacitance exceeds the predefined threshold. You can have an RC circuit here. So this triggers output to change between on and off. Okay, so you can sense and you can set the value of these oscillations. If it is below some amount, there is no object. If it is above some amount, it is close to the object. Okay, when the object moves away, the oscillator's amplitude decreases. Okay, again because change in the capacitor is smaller, and then we can change it back to the original state. If you have large and if you have large size and dielectric constant of the target, it means that larger capacitance and easier detection. Okay, so there is something called as dielectric constant which modifies how much the capacitance is changing. If the size of the object is larger, then the change in the capacitor is also large. Okay, and it is very useful to detect level through a barrier also. Okay, because you cannot go to the object because there is a barrier, but you can take this capacity of proximity sensors or find out what is the level or where the object is. Next is ultrasonic capacity proximity sensors. Okay, we can also have ultrasonic proximity sensors. Basically these are electroacoustic transducers. We send and receive high frequency sound waves here. The emitted sound waves are reflected by an object back to the transducer, which switches to the receiver mode. Okay, the same transducer is used for both receiving and emitting signal. Okay, next one is optimal proximity sensors. So we can also have this kind of sensors. These are called as light beam sensors. We have a solid state LED acting as a transmitter by generating a light beam. Okay, so a solid state photodiode acts as a receiver here. The field of operation of the sensor is the long pencil-like volume formed due to the intersection of cones of light from a source and a detector. Any reflective surface that intersects the volume gets illuminated by the source, and it is seen by a receiver. Generally, a binary signal is generated when the received light intensity exceeds a threshold value, so we can see whether there is an object point of view or not. Okay. Next one is range sensor. Okay, range sensors are typically used to measure the longer distance, not close to the robot, but objects that are much larger distance. We can use electromagnetic or electrostatic or acoustic radiation. Okay, so it looks for changes in the field or the return signal. These are highly reliable with long functional life and no mechanical parts. There are four main types of range sensing which are used in robots. One is called triangulation, one is called structure light approach. Then you can see difference in the time of sending and receiving, okay, the signal. These are called as the time of flight range finders. And then you can have a camera vision. Okay, the main application of range sensors are in navigation, in mobile robots, obstacle avoidance, locating parts, etc., etc. So now range, you can see here the basic topology. So let us look at the triangulation here. Okay, so basically we have an emitter. Okay, so it is sending out narrow beam of light. Suppose there is an object and here, and you can scan or rotate this emitter, and there is a detector which is at the distance d. This is, okay, b emitter and detector. Okay, so when you are rotating, when this object is directly in front of you will get a large signal. Okay, so the detector output is peak when the illuminated batch is in front. So if b and theta are known at the instant, we can get d as b tan theta. Okay, so if you change b and theta one, okay, okay, then one can get the object, the distance of the object at different points. Okay, but it must be visible to this light source. There is almost no computation required here. Okay, this is very very simple. Okay, now here all we need to know that what is b, and then find when you get the peak detection at the angle at which the peak detection is happening. And when we quickly know that d, which is just where we need to do okay, tan of that angle. Okay, it is very slow because we have to do one point at a time. So as you can see, if you send this beam, most of the time is scattered. Okay. So now next well-known way of detecting range or measuring the range is something called as structured light. Okay. So let us look at what it involves. So we have a source of light here, but this source of light is now generating a sheet of light. Okay, not a single beam. Okay, and let us assume that there are these objects in the scene. Okay, so how do we generate a sheet of light? Okay, like this sheet of light, thin sheet. We can generate a sheet of light through cylindrical lens or a narrow slit like a projector. So when this sheet of light intersects an object, and if you are looking at the scene from a camera, okay, at a slight angle, you will see these lines, different lines. Okay, you will see one line, one more line, and then there is a gap. Okay, and one more line, and then is a curve and so on. So the camera, which is offset slightly from the projector, views and analyzes the shape of these lines. Okay, and by using some kind of calibration and by knowing that what the shape of the line is, we can find out what is, okay, we can find out that this object is nearer to the nearer than this object. Okay, and we can even get a sense of distance by calibration. Okay, now so the distortion of the line is related to the distance and can be calculated. Okay, the horizontal displacement in the range is proportional to the depth gradient. Okay, is to give some more information. So an integration also gives absolute range, and we need to calibrate, okay, to obtain the distance, the range. Okay, it is very fast advantage where little computation is required and can scan multiple points or entire views at once. Okay, the big thing is that you should be allowed to shine a sheet of light in the scene, otherwise this whole thing does not work. Okay, now time of flight for range sensors. So the time of flight sensor works basically with the idea that you send the pulse signal either from a laser or an ultrasonic device. You find the time taken by the pulse to return from a surface from where it is reflecting. Okay, so if D is the target distance, then C is the speed of the radiations and T is the elapsed time. Okay, CT. Then D equals to CT upon T, where D is the target distance, C is the speed of radiation, and T is the elapsed time divided by 2. So for light, this is not very useful because C is very large. You know that it's 3 into 10 to the power 8 meters per second. Okay, but it can be used for measuring large distance because it is, because suppose if it is very close, this elapsed time will be very small. So if you want to, as an example, if you want to measure a range of within plus or minus 0.25 inch accuracy, we need to measure time intervals of the order of 50 picoseconds. Okay, which is not very easy to do. However, this idea can be used for acoustic or ultrasonic radiations. Okay, but why? The reason is because this C is much more smaller. Okay, it is 330 meter per second. Okay, as opposed to 3 into 10 to the power 8 meters per second. This time of flight sensors can only detect distance at one point in its view from whether the reflection is happening or not. And if you want to and if you want to find the different distances, we have to scan this object. Okay, now another way of using the time of flight is by modulation. Okay, so the idea of is the following: instead of measuring the time of flight, we will measure the phase shift of the beam. Okay, so we have a laser beam. Okay, you can see a laser beam, and then at some L, okay, of the detector, then we split the beam into two ways. Okay, one directly goes to the phase shift decoder. Okay, one directly goes to phase shift decoder, and one goes to the object and gets reflected. Okay, this is how it works. So the phase delay between the two beams is measured here. So the distance traveled by the first beam is basically L. The distance traveled by second is D, and which is L plus twice D, and D cap and D dash equals to L. Okay, you can see here D dash equals to L plus theta upon 360 lambda, where theta is the phase shift. Okay, so if you can measure the phase shift, so for theta equals to 360 degree, the two waveforms are aligned, and d dash equals to L, and d dash equals to L plus n lambda. Okay, the waveforms cannot be differentiated on phase shift alone. Okay, here you can see. So I mean, so if you restrict, so if you restrict theta to less than 360 and 2d to be less than lambda, so then this distance is directly related to the phase shift theta. In fact, this expression, okay, so I mean now, so I mean no, so if I know the wavelength, I can measure the phase shift and I can find the distance. Okay, so typically lambda is very small. It is impractical again for robotic applications. So lambda of light is very small. It is of the order of some microns, but we can modulate this laser light. This is what I meant. Okay, so we can modulate that beam with a waveform of much higher wavelength. For example, if the modulating frequency is 10 megahertz, okay, then this lambda is c upon f, that is 30 meter, and the distance up to 15 meters can be now measured. Okay, the advantage of this continuous light technique is it yields instantly intensity. Okay, it will yield intensity as well as the range information. It requires very little computation, and lasers do not suffer from spectacular reflection. Okay, specular reflections. It is expensive. Okay, and it is not that robust. It requires much high power. Now, range sensors for ultrasonic. Okay, the range sensor which are ultrasonic are very similar to the pulse laser. Instead of a light pulse, okay, we generate ultrasonic chirp. Okay, which is transmitted over a short time period. From the time difference between the transmitted and reflected wave, D can be obtained. Okay, it is generally used for navigation and obstacle avoidance in robots. You remember the speed is much smaller. Okay, so we can find out the distance closer. It is much it is much cheaper than laser range finder. Okay, shorter range is more desirable. If you want to measure large distances, these ultrasonic waves of disperse. Okay, and you will not get very good signal. The wavelength of this ultrasonic radiation is much larger. Unfortunately, it is not reflects from, okay, very well from small objects and corner. So I cannot use these ultrasonic range sensors if the object is very small. The ultrasonic waves are not also not reflected very well from the plastics and some other materials. So if you have lots of plastic in your environment and you have ultrasonic range sensor, it will give sometimes harmonic results. Okay, and then next one is the vision sensor. finally we have vision sensor. Okay, as I have mentioned earlier, it is one of the most powerful and complex form of sensing. Okay, it is analogous to humanize. Okay, it comprises of one more video cameras, okay, with integrated signal processing and imaging electronics. It includes interfaces for programming and data output and a variety of measurements and inspection functions. This technique is also sometimes referred to as machine or computer vision. Okay, this technique, there is a whole field called computer vision. Okay, there lot of works or lot of research and lot of papers in this area is going to happen and are happening right now. Okay, and then a large amount of work, computer work, is done in this area. Okay, earlier, because the computation required are very large compared to any other form of sensing. So instead of proximity or laser sensor finder, okay, or any other different techniques, cameras require a huge amount of computation, and only very recently we can have processors which can process the measurement by a camera, and it will obtain good estimate of the distance. So now these computer visions can be subdivided into six main areas. Okay, first is sensing, then pre-processing, then segmentation, then description, then recognition and interpretation. Okay, so this segmenting is very important part in computer vision. Okay, this takes quite a bit of time. So if I need to know where there is shade and where there is image, where the reflection is, okay, we need to know the edges. That is what is called segmentation. And you can find some more description. Okay, then you need to recognize the object, and then you need to interpret. So each of these requires a huge amount of significantly, okay, large of amount of computing. There are three levels of processing. Okay, we have low level vision, okay, which are primitive in nature, requires no intelligence on the part of the vision functions. Sensing and pre-processing can be considered as low level vision functions. Okay, medium level vision are what we expect. Okay, characteristics. Okay, and label components in an image resulting from low level visions. This is the second stage. It requires segmentation, description, and recognition of the individual objects in this stage. Okay, so it is the cube or it is the sphere we need to recognize. So there are some of the medium level vision functions. Okay, also, and the high level function is basically want that we want to emulate cognition. Okay, looking at the scene, once we know it is a some object, we can infer something or can be taken action based on that. So that is what cognition is. Okay, so there are increasing number of robotic applications using vision sensors nowadays. This is primarily due to the increase in computational capacitance, okay, computational capacity and low cost of camera. So there are now cameras which are very cheap and which can be used for computer vision. The vision system can determine the distance of the objects. It can determine the geometrical shape and size of the objects. Okay, it can also determine color, the brightness, the properties of objects. Okay, it can be used for navigation. It can be used for to make a map. Okay, Google Maps. It can be used to do obstacle avoidance. It can even be done for Cartesian position and velocity feedback. Okay, so if I know the distance, I can somehow obtain the estimator velocity. Okay, it can be used to parts. Okay, and many other usage. The vision system can also learn about the environment. That is, there is a lot of research going on to automatically, okay, do this medium level segmentation and trying to figure out what the object is. It can also be used to acquire knowledge and intelligence. Okay, Vision systems are extensively used in autonomous navigations in mobile robots. Okay, Mars rovers in the simple example. Okay, you know the robot is moving around in the Mars. There is a time delay between the signal coming from the Mars to JPL or wherever it is controlled from. Okay, so in between it must do something and autonomously. Okay, the signal gap, because it cannot wait for the instruction always from the earth. Okay, so that is what is called as autonomous navigation. So a camera is there which will which you will see, okay, whether there is a ditch in front or not while it is moving. If there is a ditch in front, it can take some decision. It will stop, it can go around. It is also seen in self driving cars. Nowadays there are many self driving cars which are coming up, and they had vision cameras, okay, which can sense whether there is a person in spot or not, or whether there is another car in front or not. Okay, or I even can sense whether there is a green or light or red light at the traffic intersection. So the use of vision systems is increasing rapidly nowadays, and as the technology improves, it is expected to become more and more mature. Okay, day by day there will be many more uses of computer vision in vision technology. Okay, now we will end this part of main elements of robot by using this slide. Okay, that is sensor based robotics, asimo. Okay, one of the sensor example of a sensor based robot, a very well known example, this is called as asimo. Okay, it stands for advanced step in innovative mobility. Okay, so basically it is a humanoid robot developed by Honda company, car company. Okay, Japanese company. You know, it is very far from their normal line, okay, of business of making good cars. So this robot which is shown here, it looks like a humanoid. Okay, half human half robot. It has legs, it has arms, it has head, in which there are a lot of sensors. Okay, there are sensors of vision, speed, balance, force, angle, and foot area. It has 34 degrees of freedom controlled by servo motors. Okay, there are 34 joints in this robot, and they are all controlled by servo motors. This robot is capable of walking, okay, running. It can maintain posture and balance. It can climb stairs to avoid obstacles. So in this example, you can see that it is trying to play soccer. Okay, in this example here, it is climbing the stairs. Okay, here in this example of climbing down. Okay, but it can climb up also. It is capable of having some intelligence. Okay, basically what is the level of intelligence it has? Okay, that is the question. Okay, so it can chart a shortest route from one point to another, that is point A to point B, using the cameras. Okay, it can recognize moving objects. It can take decisions. It can differentiate sounds and recognize faces and gestures. So if it is talking, it can turn towards you. If you are talking, then it can shake hands. So there are these example of these robots. Okay, shaking hands with very distinguished people on its own. So this is one of the best example of sensor based robot. Okay, so summary, okay, of this lecture. So in this summary, the main elements of robots are links and joints. Okay, actuators are transmissions. Okay, sensors and computing elements. The robot is very expensive equipment and sophisticated, and with expensive components. Okay, the sensors and computing intelligence to the robot and more. Okay, of the sensors and computing are being employed in these robots. Sensors, computing, and algorithms make up more than 60% of the cost. So you might think that the motors are very expensive. That is not true at all. The sensors, computing, and algorithms which go into the making of intelligent and autonomous robot is almost 60% of the or more of that cost. Okay, So we will stop this lecture, and we looked at the main elements of a robot. In the next lecture, we will look at some of the modeling and analysis techniques used in robots. So till then, take care, have a nice day, and do watch this video. Goodbye.